Our approach when we investigate randomization in the context of computation is the same as what we've done before. We're trying to group together or identify classes of problems that can be solved using randomization in specific ways. We will have a few different such classes depending on what type of results we allow. The first class we want to discuss is called randomized polynomial time, or RP for short. And it looks sort of similar to the definition of NP we had, where instead of certificates we use these strings of random bits. The difference is the following. Before, we were happy if there was a single certificate, which means there might have just been a single string that makes the Turing machine accept in case the word is really part of the language. But of course, if we just generate the string at random, then encountering that single proof or certificate might be very unlikely. So the probability is larger than 0, but barely larger than 0. And that might not be super helpful if we really want to do some suitable computation. So for this randomized class RP, we have exactly the same definitions as for NP, but we require that not just a single string works, but at least half of all possible string works. So if we pick a random string, then the probability that the machine accepts, in case the word is part of the language, should be at least 1/2. So if x is in L, then the probability that M accepts x combined with a random string of bits of polynomial length should be at least 1/2. Still, we require that the machine always terminates in polynomial time, and still we require that the machine always rejects if the word is not in the language. If there is a machine that has these properties for a specific language L, then we say that that language L is contained in the class RP. So suppose you have a problem in this class RP and you have the corresponding Turing machine that has this claimed property. Then you get some input, you run this Turing machine, and the Turing machine rejects the input. What do you know about the input in this case? What about if the Turing machine accepts the input? What do you know then about this particular input? So one thing to realize is that this machine will not always give you the correct answer. Sometimes the answer you get might be the wrong one. It's just that the probability that you get a wrong answer is somewhat limited. For this class RP, we have the property that we never get false positives, meaning that if your machine returns the answer, yes, I believe this word is in the language, then that is always correct. You can rely on that for sure. But if the machine returns that a word is not in the language, then that might be wrong. So the machine might produce false negatives. It might say no, although the true answer is really yes. Again, for the class RP, we never get false positives, but we may get false negatives. Think about this carefully, because it's easy to get tripped up by this. Because if we look at how the class is defined, we say if x is in the language, then the machine accepts with a probability greater than 1/2, or at least 1/2. If the word is not in the language, it rejects for sure. So it seems like the reject decisions are the ones that are always correct, and the accept decisions are the ones that are sometimes wrong. But that's not true. If you think about it carefully, you will see that it's exactly the other way around. Next, we want to compare RP to some of the complexity classes we've already seen. Let's start with the complexity class P. How do P and RP relate to one another? Maybe pause for a minute and try to think about the relationship between P and RP. What can you say about it? Hopefully you have realized that if a language is in the class P, it also has to be in the class RP. And this is because if you have a deterministic Turing machine that decides a language in polynomial time, then surely a probabilistic Turing machine can also decide the language in polynomial time. The Turing machine simply doesn't use its extra power of randomization. You don't have to use extra random bits. You can just ignore them. You can either not generate them in a probabilistic Turing machine, or if they are fed to you from outside, you just don't look at them. You just do the same thing that the deterministic Turing machine would do, and you can decide exactly the same stuff. So RP can only be more powerful than P, or it may be equally powerful, but it cannot be less powerful. So all of P is contained in RP. Next, let us consider the class NP. How does it relate to RP? Maybe again, pause for a minute, think about the relationship between RP and NP, and what can you say about those two classes. Hopefully you see that RP has to be completely contained in NP. The definitions of RP and NP have been very similar, and the only difference is that if a word is in the language, in one case the machine accepts with probability at least 1/2, and in the other case, for NP, the probability to accept has to be positive, but can be very close to 0. But clearly, a Turing machine that satisfies the first condition also satisfies the latter condition. If I accept with probability at least 1/2 if the word is in the language, I also accept with a probability that is positive. And therefore, any machine that satisfies these conditions for RP would also satisfy the conditions for NP. So any problem that is in RP, we can use the same machine that shows that that problem is contained in RP to argue that it is contained in NP as well. So the complexity class RP is contained in NP, and the complexity class P is contained in RP. So RP somehow lies in the middle of P and NP, somewhere in between.